We've looked into the Ohm's law just briefly already when we talked about resistors. So now it's time to dive a little deeper into that, and also to look at how we utilize diagrams to show how a circuit is set up. When we talked about resistance, we used this equation delta V over I as part of our definition for resistance. The idea was that if we have a big drop in energy, we would expect that we'd have a lot of current flowing. But if it doesn't, that must be an indication that the component we're trying to have the current flow through has some property to it that makes it difficult for current to flow. So we looked at resistance as this ratio between potential difference or voltage drop across a component and the current going through it. Now, it'll kind of make more sense conceptually to rearrange this one into I equals delta V over R. So again, if we have a large value for potential difference for voltage drop, we'd expect I to be large. If we have resistance that's very large, we'd expect our I to drop off then. And then this phrasing we usually refer to as Ohm's law. So Ohm's law will use the I here to mean current in amps. That is running through this component, whatever it is we're investigating. Delta V is the potential difference, or the voltage, and that'll be in volts, that we have across this component. And then R is going to be the resistance of the component itself, measured in ohms. Now this relationship requires that we have our resistance, or the ratio between I and V, be some constant value. So if we double the current, we would expect to have double the potential difference, or vice versa. So that happens for some materials. It doesn't happen for others. Materials where R is going to be a constant value, doesn't matter how much voltage we put across this component, the voltage to current ratio will be the same. We call those ohmic materials. So it doesn't matter how big the voltage is, the current and voltage will have this constant ratio, so R is a constant value. Now when would that not happen? It turns out not to happen when we have large amounts of thermal expansion. So if we have some component that gets really hot when we have a current running through it, and it actually gets bigger as a result of getting hotter, that will tend to change the value for R. Now this actually happens for all materials. When we talk about an ohmic material, that's really an approximation. It still changes a tiny amount. It's just such a small amount that we neglect that change. Now, there are certain materials that we won't want to neglect that change. So for example, when you turn on a light bulb, the resistance when you first turn it on is one value, and then as that light bulb gets hot, as the filament gets hot and expands, that resistance is going to be a different value. So those two are going to be fairly significantly different, and so we're not going to want to treat that as an ohmic material. Instead, we call it a non-ohmic component or material there. Now, as we get into more complicated circuits, it's not going to be very easy anymore to describe in writing what the circuit looks like. We'll move beyond just the one battery connected by wires to a one resistor, so we need a better way to show this. So we have a few symbols that we're going to use consistently here. So the first one that we need to know is just a line. A line is going to be used to represent a wire. If we have a line with some squiggles in it like this, that's going to be used to represent a resistor. And then if we have a line with a big and then a small perpendicular line like this, that's representing a battery, or some voltage source anyway. And then a little more detail on this battery, we have one long line and one short line. The long line is going to be the positive end, the short line is going to be the negative end. Sometimes you'll see something that looks like this, with a couple long lines and a couple short lines. This is used to represent a multi-cell battery, which really all batteries that we would deal with for the most part are multi-cell batteries. I guess the little button cell ones aren't multi-cells, but like AA batteries are multi-cell batteries. So pretty much all batteries that we would actually work with would be these multi-cell batteries, but if you don't know the distinction at this point, that's not a big deal, so don't worry about it. Just know that you might see either symbol here, but either way it represents a battery, and we can tell the positive side from the negative side by looking at the lengths of those lines. So here's a pretty straightforward example that you might see with using Ohm's law. We have a battery with voltage given connected to a resistor with resistance given, and looking through the current. Now, probably just as frequently you would see this given as a diagram, and then they might label the resistor, and they'd ask, what's the current through resistor R1, for example. So let's just diagram that quick. We've got a 1.5 volt battery, so I draw that as a long line and a short line here. Usually we do the batteries on the left side, but that's just a convention. It doesn't always happen that way. And then we have a wire that leaves the battery, and we typically draw right angles for our turns in these circuits just to kind of keep things orderly. So I'm just going to draw a wire all the way over here to where I have my resistor. I'll call this R1, and it has a resistance of 150 ohms. And then my battery has a voltage, delta V, of 1.5 volts. Alright, 1.5 volts, that means that if we looked from this point to this point, we have a change of 1.5 volts. We'll talk a little bit later on about Kirchhoff's rules. That's going to mean also that from this point to this point, we're going to have a change of 1.5 volts. So when we talk about Ohm's law, we have to look at one specific component. I can't look at the voltage across this battery and the resistance of this resistor. I have to work only with the battery or only with the resistor. And with the battery there, all the battery does is maintains a constant potential difference between these 2 points here. And since we have nothing but wires from here to this end of the resistor, we're not going to have any change in voltage or any voltage drop there. We have nothing but wires from here to this end of the resistor, so that constant 1.5 volts is being held across these two ends of the battery as well. So if it's helpful, you can write in here delta V1, that's going to be 1.5 volts also. And then we're going to look for the current here, so I'm going to use Ohm's law. I equals delta V over R, which in this case is 1.5 volts divided by 150 ohms, which is going to give a current of 0.010 amps.